Significant figures is a topic that I just think it's good for you to be introduced to, because in chemistry and in physics, we spend more time with significant figures, and it's something that we just need to kind of be familiar with, because it's just a big deal in like the science world. Okay, significant figures is a big deal. Have you heard that term before? Significant figures or significant digits? Those mean the same kind of things. Okay, so significant figures and significant digits mean the same. But significant figures basically tell us how precise our measurement is. Okay, so we're kind of going back into the measurement realm, but we still have to learn how to do math with them. So it basically is telling us how precise a measurement is. All right, so if I go take a measurement, let me just give you an example here. Let's think about our examples with using a meter stick. Okay, if I use a meter stick, and this is 16 centimeters, and this is 17 centimeters, and let's say it's marked to the 10th place. Okay, so let's give an example here that my object is this long. If I was going to take a measurement with a meter stick that's marked in this way, can you give me, what's the correct measurement here? 16 point... 6, 7, 8, 16.8, maybe 8.5, maybe 8.6, maybe 8.7, somewhere in there, but 16.86 centimeters. Because I read that it's larger than 16.8, but less than 16.9. Would we agree with that part? And then what's my last digit right here? 6, but what is it? What kind of a measurement is it? Did I know that for sure, or did I estimate that digit? I estimated. Didn't I take a guess on that 6? Right? It could have been 5, could have been 6, could have been 7. The last digit is an estimate. And so in this particular measurement, I've got 4 significant figures, okay? And I'll talk with you about what those mean. But essentially what a significant figures tells us is that if I reported this measurement as 16.86000, would that be a valid measurement? Can I do that? Can I just add zeros onto my end of my measurements like that? No, because it makes my measurement look more precise than it actually is, right? It makes my measurement look more exact than it actually is. But do you guys see what I'm saying there? I can't just tack on zeros at the end of my measurement, because it leads to a false sense of precision, right? My measurement tool was not exact enough that I measured to here and I estimated that digit, right? That wasn't the case. It was only exact to the 10th place, and I estimated to the hundreds. So that's why we use significant figures. It keeps us from reporting measurements and calculations that are more exact than what they actually are. Okay, so that's kind of the big picture for significant figures, okay? So when we talk about significant figures, not all figures are significant when we take a measurement. And I know that might seem a little bit counterintuitive, but I'm going to show you a bunch of rules here for significant figures, okay? Rule number 1 says all digits that are not a 0 are significant, okay? Are these written down for you in your notes, or do you need to write in these rules? You need to maybe write these ones in, okay? Rules for significant figures. The first rule is that any digit that is not a 0 is considered significant, okay? And that's because we put thought into that number, right? We either estimate it or we read it exactly. So any non-zero digit is significant. If I asked you how many significant figures are in the measurement we just took, how many would you tell me? How many sig figs are present?
4.
1, 2, 3, 4. All 4 of them are significant, because are any of those digits a 0? Nope, right? So rule number 1 says any digit that's not a 0 is significant. You will notice that zeros is where we've got some gray area. And that's where we really define our rules, is that if there's a 0 in our measurement, we've got different rules that deal with zeros. But any number that's not a 0 is always considered significant, because we wouldn't just throw a 7 into our measurement for no reason, right? Same thing, we shouldn't throw any number, but we wouldn't do that. All right, next rule says zeros to the right of digits after the decimal point are significant. zeros to the right of digits after a decimal point are significant?
Four.
1, 2, because they're non-zero, and 3, 4, because these zeros come to the right of digits after a decimal point. They come to the right of digits after a decimal point. These zeros right here are telling us that the measurement we took, we think is exactly 13.00, right? We won't add zeros to the end of measurements unless we're, number one, allowed to, right? If our measurement tool allows us to put a 0 on the end, we do it to show that we think it's exactly on 13. Does that kind of make sense? Okay, so that would be 4 significant figures there. Okay, what about this number right here? How many? 4, right? All of them. 1, 2, 3, and 4. What about this one? 2. Yep, just like that. What about this one? 5. 1, 2, 3, 4, and 5, right? That 0 is to the right of digits, and it's after the decimal point, right? It comes after digits, and it's after the decimal point. Are we good with that? Mm-hmm. Okay. All right, next rule says zeros between digits are significant. Zeros between digits are significant. That just means it's a part of the number, right? It's just part of the number at that point. So 104. That 0 is not anything we added in there arbitrarily, right? It's just part of the number. So how many significant figures would this one have?
3.
1, 2, 3. Yep. It just now is a part of the number. What about this one? How many sig figs? 6. 1, 2, 3, 4, 5, and 6. Right? You'll see all of our rules are structured around zeros. So we've got to figure out where they are and how they apply with each rule. Okay, are we good with these 3 so far? Yep. Okay. I think it might be good for you to write down some of the examples I'm doing as well. But zeros to the left of digits are considered non-significant. And I want you to write in one extra thing here. 0 to the left of digits before digits start. So before they start. Zeros to the left of digits before they start are non-significant. They are just considered placeholders. And I'm going to show you an example of what I mean with that. Okay, so let's see if we can apply this rule here. If we're trying to apply this rule, if we're trying to think through what this rule means, how many significant figures would you guess are in that measurement?
5.
Okay. Anyone else think 5? Raise your hand if you think 5. Raise your hand if you think 6. Raise your hand if you think it's neither of those. All right, here's our rule. Zeros to the left of digits before they start are non-significant, right? These zeros all come to the left of digits, okay? They are non-significant. So here we have 1, 2, 3 significant figures, and that's it. So let me explain why. They're considered placeholders for the decimal place. So if this is my measurement, wouldn't it have been a better idea for me to just measure in centimeters or millimeters instead? Right? See how small of a measurement that is in meters? It would have been better for me to just use a different measurement tool or a measurement unit, right? That all those zeros are doing are showing me how small the number is, right? I didn't put thought into those zeros. I didn't add them on to show how exact my measurement is. All it is it's showing me is how small they are. So these zeros, whether they are in front of or behind the decimal, if they come before any digits start, are non-significant. So here we only have 3 significant figures. Okay? So what about this one? Okay, you might want to write down some of these examples that I'm doing. 3. Very good. Okay, so let's look at this one. We have 3 significant figures. What are they? What are the 3 that are significant? 2, 6, and 0. So why is it that this last one is significant? It's to the right, and it's after a decimal. But these 2 right here are non-significant. Now, we can't just take them off. We can't just remove them and say our measurement now is 260. Right? Because it's still telling us a part of the number. It's still telling us that it's a small value. But we say in terms of significant figures, there are only 3 there, right? These are non-significant. Okay, we can't just erase them. We can't remove them from the number, but they are not considered significant in our measurement. Okay, questions with that rule? That one's kind of tricky. Okay, the last one is that all digits used in scientific notation are significant. And I want to maybe add one little thing in here. I want to say all visible digits. And I'll tell you what I mean when I say visible digits. All visible digits used in scientific notation are significant. All right, so what I mean when I say that is let's write out some numbers here in scientific notation. Okay, 3.4 times 10 to the third. Okay, 3.4 times 10 to the third. Now, when I'm asking about significant figures, I only care about these digits right here. That's it. I do not care about what the number looks like when it is expanded out of scientific notation. I just don't. I only care about what is visible right here. And so how many significant figures would I have?
4. No, 5.
Just 2. I only care about this right here. I don't count any of that when I'm talking about significant figures. It's only the digits that are visible right here before the times 10. We don't include that times 10. Okay, it's just the digits that are visible. So it's just 2 significant figures there. Okay, what if I had a number that looked like this? 3.60 times 10 to the negative 6th. How many significant figures would I have? 3. 1, 2, 3. I don't care what it looks like when we expand it out. Right? When I actually move that decimal, I don't care what that looks like. I just want to know in scientific notation how many are there. Okay? All right. Let's try a couple more examples here before I get to the next set of rules. Okay? Let's try some examples. Give me the number of significant figures. Tell me how many sig figs are in these measurements. I'm going to write several up here, so don't shout it out just yet. On the first one, what do we think? 3. Yep. Perfect. Just the ones that are visible right there. Just 3. Okay. What about in the second one? 4. 1, 2, 3, and 4. Why is this 0 right here significant? Right. Okay. So not just because it's to the right, it's because it's between digits. Now it's just part of the number. Okay. So it's between digits. It is also to the right and it's after, but it's between digits. That's really the rule that we're applying there. And then what about this last one? 3. And so why is that 0 significant? It's to the right and it's after the decimal place. Yep. Okay, so do we feel okay about identifying the number of significant figures? This easy peasy? Okay, very good. Let's look at now what happens if we're not sure. There are some numbers that lead us to be unsure of how many significant figures there are. Okay? I'm gonna actually skip through some things here. I'll put them up here. Okay. The example that I can think of, well, there's a lot of examples of ambiguous number, but the example I'm going to give is this number right here, 120,000. 120,000. 120,000 has what I call trailing zeros. Okay, is any of this on your slides, or do you have to write this whole thing down?
We have to write the trailing zero.
Okay. All right, 120,000 has what I call, and I don't know if that's a real term for it, but I don't know. That's what I like to call it. But it's trailing zeros. And trailing zeros are zeros that are at the end of a number without a decimal point. Okay, trailing zeros are what I think are zeros at the end with no decimal point. And the reason that they are a problem is because we don't know how exact this measurement actually is. We don't know was this measurement supposed to be 120,000.00? Or was this measurement 118,764 and it got rounded up? Right? We have no idea the level of precision of our measurement here because we don't have a decimal place. And it's just been rounded like crazy, right? We just don't know. So ambiguous numbers are what these are called. They are called, this number right here is called ambiguous. Okay? This is zeros without a decimal place. Okay? Zeros at the end without a decimal place. So other examples of ambiguous numbers, it's any number that's got a zero at the end with no decimal. Right? So 10 is ambiguous. 70, 700, 4,000, all of those numbers are ambiguous. 460, right? Anything that's got a zero at the end with no decimal place is considered ambiguous. So if I were to ask you to identify how many significant figures are in that number, you wouldn't even need to take a guess. You would just tell me it is ambiguous, right? You can abbreviate it just like that. Okay, so zeros at the end with no decimal place would be considered ambiguous. Okay? Tell me, what other questions do we have there? Okay. Now, let me tell you this. When we're doing math problems with significant figures, we're going to do our best to not give answers that are ambiguous. Okay? So how can we fix a number that's ambiguous? There's two ways we can fix a number that's ambiguous. We can, first of all, we can add a decimal place to it, right? And add a zero after the end. But the second way, and the more common way that we fix ambiguous numbers, is by putting it into scientific notation. That's the most common way we fix an ambiguous number. Okay, because we're going to go through some rules with math here in a little while, but we're going to go through how we know how many significant figures our answers can even have, right? But the most common way for me to fix an ambiguous number is to put it into scientific notation. That's really important. Okay? All right, I would like for us, we're going to actually do a little game here because I think I want to stop with the notes for today.